Yeah, so pure awesomeness number 2, speed and energy. So this is just me, like, you know, I don't work for these people, but I just thought the charts are really cool. So like, check it out. The, I mean, this is, what is it? Yeah, the thing that you really need to know is that red is energy efficiency of the pruned network, and speed, red is the speed, what's this thing called? Yeah, GPU pruned, so I mean, like, the GPU prunes get a massive speed up for these various, like, Alexander and VGG nets they presented before. Again, for every network they present, I don't know how many they threw out, so like, I mean, everybody kind of inflates their statistics, look kind of nice, but still, it's pretty awesome. I did not get these results, but I did get good enough results to like be enthusiastic about presenting the paper in this setting. So yeah, you get.
What's TK1?
TK1.
Yeah, CPU.
So
TK1.
is it? It's not. Is it the tensor processing unit? Let me. Don't know. Maybe it's another chip. It would be my guess.
Video cards that come in.
I'd have to check.
I think it's the lower end video card, these
Yeah.
first generation.
I will check, but it's in the paper itself, which, by the way, we're not going to do this lab actually because we don't have time, but I'll show the name of the paper again really quick. No, I won't. Yes, I will.
Team win.
F5 or F11.
To scroll this up or down, is it?
What do you want to know?
Just it. Oh, okay. There you go. That's all I want.
Oh, page down quick.
Okay.
Page down.
Okay, sweet. So yeah, the deep, or I'll go page up again really quick just to show the name of the paper. Yeah, deep compression, compressing deep neural networks with. So just Google it. It's on. Free. So the next thing I want to show is the paper behind pocket flow. So we won't do this lab. If we did, basically it would be doing gradient descent in NumPy. Yeah. We don't have time. But basically, in NumPy, you can imagine that you could implement these algorithms a lot easier than TensorFlow. But let's do the pocket flow then really quick. It's important. So, discrimination-aware channel pruning for deep neural networks. Pocket flow, which is the thing made by Tencent, is most influenced by this paper. It also cites the previous paper that I showed you. Pocket flow is amazing. But this paper, for me personally, this is one of my weaknesses, that if a paper has a lot of math where it's like multiple things that have like 5 superscripts, I have a lot of trouble reading that and just kind of understanding what it's doing. I don't know if you guys have the same problem. Okay. Yeah, so for me it's a lot easier to see an algorithm like written out, but even they don't do a good job with this. So all I can say is that I kind of grokked what they're talking about, but not well enough to present it with the same confidence that I presented the previous thing. So I'm sorry about that. I think if I took a week, I might understand it better. But the important thing to know is that this is what's under the hood in pocket flow. So without further ado, I will present the limited amount that I understood from this paper. So why discrimination-aware channel pruning? So some definitions. Channel, so you guys know, in the CompNet, it has a certain depth, and those are each channel. So RGB, like, it's like the normal one, right? But as the CNN gets deeper, whatever the network learns to detect, so like the stack in the CompNet will just get deeper or not, depending on what it's doing. And those are your channels. And then feature map, so is the output of all this stuff applied to a previous layer. So you guys have seen like online, they'll show the features actually being detected in images of like straight lines or curves or whatever. That's a feature map. They use these regrettably somewhat interchangeably in the paper, but it's just, if you guys read it, it's like, that's the definition. So, couple things. They introduced their channel pruning algorithm directly into the loss function, right? So it's like some type of regularization parameter. That's the normal way to do it, and this previous paper that I presented didn't do it this way. So by doing this, you're able to put all of it, of course, in the GPU, or at least it's part of it. That's important. And then the loss function has 2 components in it. One is maximizing discrimination, and 2 is minimizing reconstruction error. So what minimizing reconstruction error means is that the feature map, essentially it will minimize the error of reconstructing the feature map. So assuming that the features are somehow semantically important to the network, like assuming that it's really important to get vertical lines or horizontal lines, what they're doing is minimizing the loss of reconstructing that feature map when something comes out of the neural network. So it assumes, okay, these features are important because it's been trained and it's determined these features are important, so we're going to minimize screwing around with these features. That's what they minimize in the loss function, which has good results. And by maximizing discrimination, what that means is that they only keep the channels that they find causes the most difference in result from one layer to the next, so that have the most kind of explanatory power. So for example, one easy way to mentalize that is imagine that you have an image that's only red and has no GB, then it would discriminate by choosing only the red channel, right? So that's the two things that go into the loss function. Then even the algorithm has all these like subscripts and stuff that like, I mean, and this is tame compared to the rest of the paper. So like, I just threw it up here so you can get the basic idea. But the first thing that they do is they do forward pass and backward pass. Where have you guys looked into what's the DeepMind thing? Those intermediary gradients, that paper that they published on it. Synthetic gradients. Have you guys read that paper? It's a DeepMind thing. But basically, in the loss function, they introduce mini loss functions across every layer and then just aggregate them at the end. This paper does the same exact thing. So they do a forward and back pass with those loss functions, and each loss function for each different layer tries to, like it says, maximize discrimination and minimize reconstruction error of the feature map associated with that layer. So they do that here, and then that still doesn't tell you which channels to keep. All that's doing is, this is kind of minimizing the reconstruction error. This, you keep channels by whatever that algorithm says on the inside of it, which I would have to speak Greek, Latin, and a lot of other languages to. But it's a greedy algorithm that chooses, like, again, getting back to if it's RGB, it chooses that you should keep R and not G. But again, the paper is super mathy, and it would unfortunately take me more time to understand it given the number of neurons I have in my head. So let me show really quickly, is there a way to drag Google Chrome over here so I can show how
So Penguin tab, I think.
Yes.
Okay, yeah. I haven't used Google Chrome in ages, so.
So Pocket Flow, which is the leading implementation of this, it's kind of sad because at the end of the day, the only real advice I can give you for a production model is use this, and like you guys just spent 2 hours to say, like, use this. You just could have left if I said that. But it's really good, and this I've used a number of times now because it works out of the box. So open source framework for compressing and accelerating deep learning models. By the way, what is it? Yeah. I say yes. Actually.
Control plus, I think, is the easiest. It's an American keyboard. Yeah.
So, with minimal human effort, yeah. So provides an easy-to-use toolkit for developers to improve efficiency with little or no performance degradation. So it's very much in the spirit of the thing that I just talked about. Works out of the box. Do you guys know what Velohai is? It's a Finnish company. Velohai. It's a deep learning company in Finland. So they have a great tutorial on this Pocket Flow with Velohai, where just out of the box they teach you how to use Pocket Flow. So it gets started. It does it on CFAR 10. So this is the evaluation of the uncompressed model before they use Pocket Flow to convince it. It's like resonant something. They probably don't say. Oh, they do resonant 20 on CFAR 10. So this is there you go. Looking at the evaluation accuracy of that. Then they compress it using. This should look familiar to you guys from earlier channel pruning, weight sparsification, and a couple other things that go into what Pocket Flow is doing. The important thing is here. So the final accuracy is 91 point something in here. so you see, this is what I was saying to Morten before, like it gets worse before it gets better, right? Not surprised, but then it kind of, it's like a Verdi opera, like the same arc, right? So the final accuracy is 91.3, so 0.7 drop from the original. So yeah.
And what's the x-axis here?
Number of iterations.
Right. Yeah.
I assumed it was that, but I actually didn't. I didn't check, so I'm telling you my assumption. But yeah, number of iterations in time, which is where, because I just assumed that drop is kind of the thing you would expect it to be. So it works out of the box. So I would recommend just sign up for Valohai, follow this tutorial. They're a Finnish company, so you're supporting a Scandinavian bare metal company by doing it. And you can just see it compress CFAR 10, and it really works. So that is the implementation of that particular paper. So maybe the takeaway from this is that if you're, so before I wasn't talking about ConvNets necessarily, I was just talking about any arbitrary network. But here, because you're using convolutional neural networks, I saw in California at this conference Francois Cholet speak, and I had him like sign a book for me and stuff like that. Like, you don't get to see that guy every day. And he, if you want to shake my hand afterward, by the way, I remember which hand I used to shake his, so like that's like 2 degrees of separation, right? So he made a really good point that if you could design an algorithm knowing kind of what the prior thing you're trying to represent is, it's always more efficient. And I think the really cool thing about this is that because you know that you're designing it for ConvNets, and because you know that feature maps of ConvNets are supposed to constitute a specific phenomenon, then you could, in the loss function, slim the network down by focusing on what a feature map is supposed to do, meaning reconstruct the features that the original network constructed. So I think that's kind of the smart insight into this particular method. And he advocated for that as well. So yeah, I would recommend using PocketFlow. The unfortunate, so this uses CFAR thing, 10, the unfortunate thing going back to the PocketFlow docs is if you do the tutorial, which I was stupid enough to do before I found the Valohai thing, they actually ask you to download ImageNet, which I had never manually downloaded before until I followed this tutorial. It took forever because it's huge. So don't do this. Use CFAR 10 in Valohai. Of course, I mean, if you have a massively fast computer, so it's like hundreds of gigabytes, not gigabytes. So, but this works too once you get it up and running. But it just took me like days to do. So I would recommend using the Valohai one. So that's this particular thing. PocketFlow, if you just want to slim down your neural networks, it's a great way to do it out of the box. Only works with TensorFlow, so far as I know. So that's kind of a downer, right? But there you go. So flipping back with my penguin key to this. I think that's it. I would have shown you the Valohai thing before. Last shameless plug, so Meeshkan, this is a picture of our 2 GPU boxes enjoying shots in the office up here after slush, so you know they party hard too. You should come visit, or even better, join us if you'd like to be part of a small, ambitious team. And you wouldn't mind so much working with me. The nice thing about me presenting is that you've seen all my neuroses and psychoses and can reasonably evaluate if I seem like a pleasant person to work with or not. But if I do, then we're hiring, and I would love for you to see me. But I'll shut up about that and say that this is us, and this is our investment money that goes into these GPUs. That did a lot of the number crunching that helped me evaluate that the decompression thing was a worthwhile thing to present to you, and hopefully you felt it was too. So that's it. So any questions? Seeing none, thank you very much.
Any questions? Sorry. You can stay around and have some more beer. Talk.
Sounds good. I can also say just thank you very much. Thank you very much. And